presentation, I want to talk about measurement systems analysis and specifically bias and linearity. So the objectives of this presentation is to discuss the accuracy of a measurement system, describe bias and linearity with respect to the measurement system, and present results of t-tests that can be used for bias and linearity to determine if there is a significant problem, a statistically significant problem with these two things in a system. Now, some things that we're basing this presentation on are background knowledge in estimating variability as a result of maybe knowledge of gauge R&R studies, using the ANOVA approach, estimating process variation, and so forth. Understanding of simple linear regression, because that's used in the linearity tests and assessing linearity, and familiarity with t-tests and p-values. So first of all, I want to set out the difference in what we're doing here between bias and linearity and the relationships between the two. Bias considers the difference between some observed average measurement that's been taken and a master or a reference value that's known for particular parts. Okay? It kind of answers or addresses the question, to what extent is my gauge biased when it's compared to some master value for that particular part? What's the golden standard measurement for this part that I'm taking the measurements on, and how do my measurements compare to that? How well is my measurement system able to accurately assess that value and compare it to the standard? Linearity, on the other hand, is also talking to determining accuracy and discussing bias, but it's looking at or examining the accuracy of the measurements taken throughout the expected range of possible measurements. As opposed to bias, what it addresses is the following question: is the accuracy of my gauge the same for all possible sizes of the items being measured over that range? So maybe there are parts where the reference value is not the same, and there's actually some range of measurements that the part that you're measuring, the parts that you're measuring could vary over. So maybe the reference value or the master value is not the same across that range. But this is the range you have to operate in. All right, to start with, let's discuss bias and the testing of that. Bias is the difference between, again, some observed average of the measurement and some known reference value. Or again, the reference value is the accepted or master value, is kind of the golden standard for a part being measured. And to determine that, it's very important that you have some laboratory tested or some type of test where you know for sure that this is the most accurate measurement, this is the value, this is the golden standard for this particular part. And the diagram down there that you may have seen already in many other publications and journal articles is, here's what you're doing. You're taking measurements, and your measurements hopefully are normally distributed. And your average value is off from that reference value or the master value. So the difference between those two happens to be your bias. And of course, you'd want this to be very small. You'd want the bias to be quite small. That's better accuracy for your. So the observed average measurement can be found, and there's always some two schools of thought, and depending on what you're trying to measure and what you have. A single part can be measured multiple times under identical conditions, or selecting several parts that are supposed to have the same reference value, selecting them at random and measuring each part multiple times, under identical conditions. So there's several different ways you can do this, but the idea is that the observed average that you get, okay, should be very close to the reference value. You hope it's very close to the reference value. If it's not, then you've got that considerable bias. We'll talk about how can I measure how far off it is, bias is too large, and so forth. So first of all, for a definition, bias is always the observed average minus the reference value. Then oftentimes you'll see reported and want to know the percent of the total process variation that's due to the bias, or how much the bias, what percent of that is bias. So you can report the following statistics. Percent bias, 100 times, of course, the absolute value of bias over your estimate of the process variation. Okay. Now, from that, what you'll do, now you've got two things now. You've got bias by definition. Then you've got that percent bias that you can examine to see whether that too large or too small. And too large or too small is dependent upon what it is for your particular part and your field and your operating range, how large is large. But statistically, if you want to say, well, is my bias significantly different from zero? Do I have a statistically significant non-zero bias? Now, there is a hypothesis test that can be done based on the definition of bias and using t-tests. Now, complete details of this are seen in the AIAG manual, and I have a reference for that for those of you who haven't seen it, but I'm sure that many of you have. But the idea is this. What this test is going to tell you, do you have a statistically significant non-zero bias? But is it a practical difference? That's going to be dependent upon your field and what is going to be considered significantly different from zero. For example, you might have bias that is off by maybe 0.02. That might be too large in some areas, but not in others. So even though if you run this test, you still want to see, well, but how large is that bias, and is it something I need to worry about? So there are details of this test, but I'm going to show you an example of how this can be interpreted. Okay, and I use t-tests for this. Okay. So what if, after you do this, and I'll show you an example in a moment, what if you do this, you find bias is significant? You need to look for possible reasons or causes for the large bias. Some of these reasons could include, but are not, only reference value could be incorrect. Okay. Maybe if you've had an outside source that has taken the measurements for you, provided that reference value, another laboratory has tested for you, are we sure that's the correct value? Measuring device, the gauge could be worn. The calibration could be incorrect or improper calibration of the measuring device, incorrect use of the measuring device by the operator or under the different conditions. So there are a number of things. This is why it's very important that when measurements are being taken, all information is being recorded. Time, regardless of what that is, the time of day, if you think that may be important, operator, under what conditions, are these the conditions that are actually recommended that this gauge be used? So it's very important that to be able to go out and find, yes, we have a bias problem. The only way you can go back and do that is if you have recorded what went on when these measurements were taken. So that's one important. Okay. And just to illustrate quickly an example of how the percent bias can be computed. This is an example where I've taken a situation and I've created some data here. The House and Berman 1988 paper investigated power modules for a motor starter. Measurements taken are degrees C per watt, degrees Celsius per watt. To study bias, a single power module was selected and measured 10 times by a single technician. The master of the reference value for this particular module is 38.45 degrees Celsius. And the process variation from past experience is known to be 1.67. And the results are given below. Okay, so these measurements were taken. Out of these measurements, off of this part with this gauge under identical conditions, the observed average was 38.6. So therefore, the bias is nothing more than the difference between the observed average and the reference value, the master value, which the bias then turns out to be 0.15. The process variation, 1.67. So if we want to record the percent bias, that would be 100 times bias, the absolute value of bias over process variation, which turns out to be about 9% of the total process variation that's due to bias. Is that significantly large or not? That this isn't very high. It's less than 10%, but that depends on if this is going to be something significant for a particular process. All processes may be very different. So there's no set standard. Look, if it's above 5%, you got a problem. If it's above 20%, you got a problem. What is that cutoff number? And that's why in a few moments we'll provide and show you the t-test and how that can be used. Say, well, at least we could say that whether or not bias is equal to 0. Okay. Now, before we go into the t-test, and I wanted to save that for when we talk about linearity, should also be noted that the process variation, how I got that number, is generally from a gauge R&R study that has been conducted or your knowledge of the process. It's 6 times the standard deviation of the process, generally. Okay. In a gauge R&R study, the process variation would be 6 times the total variation. I'll show you that in just a moment. If several parts, now leading into linearity, if several parts are randomly selected over the expected range of the measurements, then the reference value that we have may actually be different across the parts selected. In our illustration, we're talking about a part, a single part whose reference value or master value is known, and 10 measurements are taken off of that part by an operator. What if several parts are taken, but the reference value is not the same? We have parts of different sizes, so the measurements that we're looking at are going to be different, and the reference value will be different over the range, okay, of possible sizes. Okay. That's when we talk about linearity. Is my gauge doing the same in terms of bias, even as the reference value or size of parts increase? Okay. So linearity refers to the difference in the bias values throughout the expected operating range of the gauge. So if you look at this graph that I've provided here, you're looking at average bias versus the reference value. Now, we'll be very clear about this. This is something that I think is very important. It looks like what I have here is I've got 4 parts with 4 different reference values, which is true. And what you see is the points plotted there are the points, or the average bias calculated for each one of those. Okay, each part measured several times across all of these reference values. And it looks like, wow, there's a huge difference, something very different with the part that has a reference value of 5.8 versus 2.1. But be very careful about looking at these graphs. What is the scale? Okay, look at the scale. The scale is not very different. It goes from negative 0.3 up to 0.3. So the length of that scale, okay, is not very big, even though it looks like it here. It's all in the scaling. When we look at this a little bit later on, when we've plotted the actual biases themselves for each part, this does not look as severe. So be very careful, and that's why I put that here, is to be very careful that you don't just look at the graph and say, ooh, I've got a problem with bias across the range. I've got a problem with linearity across the range of my reference values. Because what you're going to see is that in this example I'm going to show you in a little bit that this data is based on, there is no real problem. And again, you got to be careful with the misleading scale. Okay. So determining linearity is very simple. You've got bias that you're still calculating, but now for several different parts who have several different reference and master values. Using the regression line, now this is a fitted line. I don't have my little hat, as you might often see on top of the Y hat. This really, if it was just the theoretical regression line, it would be Y equals beta naught plus beta 1x plus epsilon, some error term. And we go through the idea of the normality, the errors are normally distributed, centered at 0, and so forth, which we're assuming is always true. But in keeping with a lot of the references that you'll see there, especially the AIAG manual, this is my fitted line, Y equals beta naught plus beta 1x, where x is my reference value, represents the reference value. Y represents bias, and beta 1 is the slope of the line, and beta naught is the intercept of the line, as we've had before. You can find this using several different techniques. I've given you a couple of references here that just show you the steps behind calculating the regression line. Okay? So once you've calculated slope, beta 1, we can find what we call the linearity. Okay? And again, it involves the process variation. So, and when you see the term linearity, what they're calculating there is really the slope, or the absolute value of the slope, times the process variation. When you see in prints or an output and so forth, you may see that percent linearity. Well, what they're doing there is they're just taking 100 times the absolute value of the slope, which is in percent, of course. And again, a flatter line or a small slope, a slope close to 0, indicates very little change over the expected range. And that's really what you want. you want your gauge to be doing the same, performing the same over all possible sizes of your parts and different reference values. Along with setting a line and calculating how these values are calculated that you often see, you might look at the coefficient determination. All this can really be do is assess the proportional tool variability that's explained by the regression line, which again involves your bias and your reference values. It can be used as a measure of goodness of fit. Okay, and you want an R-squared value. You know it should be quite high if our line is supposed to be significant and very low. If you want a straight line, which is generally what we want, meaning very little no slope. Also, what you may want to do is do a hypothesis test to determine the validity of this linear relationship. Because again, looking at the eyeballs view or just calculate percent linearity may not tell you the whole story. You say, well, I've got the slope is small, so my percent linearity will be small. Well, that's good, but how small is small? Right? So we could do approximate t-tests and look at p-values to make the decision. So we're basically testing the hypothesis that beta 1 is equal to 0. My slope is 0. Our goal is that we want the slope to be practically 0, meaning that the bias, again, because you're looking at bias across the reference values, if you've got a significant slope, that means that biases are increasing or decreasing depending on which direction as you go across the parts. Okay. Slope being practically 0 indicates no significant increase or decrease in the bias of the range. Again, a significant increase or decrease, beta 1 equal to 0. This again, if you're able to not reject this null hypothesis, which is what we want. We want to not reject this null hypothesis. Then you still want to look to see, well, maybe I should investigate and make sure I look at my bias values anyway, and I'll show you that in the example. Even though, as you're going to see, bias and linearity turn out to be insignificant, it's not a real problem. When you look at the individual bias across the parts, you may want to go back and investigate, well, there's something else going on with the variability. We'll talk about that in just a moment. Okay? So what if you do run these tests and everything, you find linearity is a problem? Again, you want to go back and investigate what could cause this. And again, this is a very small list compared to what could actually be going on. Was there some error in the reference value? Was there a proper calibration of the gauge of the instrument? Wear out again? How is it collected? Are you using, the correct reference value and so forth? So any number of things. But again, if proper records are not kept when the measurements are being taken, then it's going to be very difficult, or it could be very difficult to go back and say, well, what caused this, or why is this happening? Okay, let's look at a different illustration, a very generic one, so that we can all kind of grasp onto it. Say that there are 4 parts chosen throughout an expected range of the gauge. Here are the range of reference values, measurements that could be taken. Okay, each part, and there are 4 of them, were measured, and over the range of this, the operating range, excuse me. But we also had that each part was measured under conditions that we know the exact reference value. Maybe it was contracted outside, another laboratory did the testing, or we know for sure what the golden standard or what the master reference value is for each part. Okay, and those are recorded in the table that you see there. Each part is measured by the same operator, say 10 times each. And this is the result of the entire study. Okay? So we have our reference values ranging from 2.1 to 8.5. Wow. And we end up with 10 measurements on each. So let's look at bias and linearity for each of these. Okay? All right, so part average is calculated. So we need to get the average measurement for each part, and that's what you see where it says part average, 2.01, 2.89, and so forth. Then we can calculate the bias. The bias, again, being the part average minus the reference value. Then you can also calculate the range, which you'll often see is recorded and people would use as a measure of process variability. Our recommendation is that, if possible, if you've got something set up like this, is to actually look at the gauge R&R, look at the ANOVA approach, get a measure of the process variation from the gauge R&R study, which I'm going to show you right now. So, but the range is often recorded and used to estimate process variability. So I included that just for convenience. What we did instead was we looked at a one-factor gauge R&R. You might look or use under some statistical packages, they have a cross gauge R&R for ANOVA. That's what we did, but using only parts. And what you'll get is you'll get an ANOVA, you'll get a whole study on process variation, and you'll even get this part that you see here. Source, you've got total gauge R&R, you've got repeatability, part to part, and then total variation. Notice we don't have reproducibility, but we only had one operator. Okay, if we had more than one operator doing this, we could include reproducibility also. But what I want to point get your attention to is that value that's the 6 times SD of the study variation that you see there for total variation. That's the process variation that can be used to calculate the percent bias and the percent linearity. And that's what you want to get. This will give a better, a more accurate estimate of variability than using any type of approach with the range. Okay? If this is possible to do. Okay? And here's the printout of a particular stat package that I used. And what I wanted you to notice there are a couple of things. Let's look at this from left to right. Look at the graph on the left-hand side. You've got your actual bias values plotted against your reference values. Now, again, what I want you to see on here is notice the red dots. There's 4 of them. Those are the same red dots that are in the graph that I showed you earlier when I said, watch out for the scaling. Now look at this when you have a different scaling, when you're looking at all the possible biases here. Okay. What you have is you're looking at is very different. It doesn't look as extreme, or the average bias doesn't look as extreme as it did before. Okay. Now what you're also saying is you see the bias is actually plotted. And it looks like, as you notice, as you move from left to right, that the biases are starting to increase. The variability in there is increasing. But the averages are different. And that is actually what a lot of people are using. That's what's used to calculate biases or significant bias problems afoot. So we'll talk about the interpretations of this in just a moment. Now, on the right-hand side, you get a couple of things printed out for you. Look at the gauge linearity. Okay, under there it says predictor, it says constant, slope, it says coefficient. What they're giving you there are the results of the linear regression, the regression line being fit between the bias and the reference value. And what we want to look at specifically is the slope, the p-value on the slope. Remember, and I've labeled that A. Remember, that's the p-value saying whether or not you can reject your null hypothesis, which is that the slope equals 0. This p-value is so large, it's 0.4. This p-value is so large, we cannot reject that null hypothesis. The slope could basically be 0. It's very close to 0. It's not significantly or statistically significantly different from 0. So therefore, what that says is that we do not have a problem of linearity across the parts in terms of average bias. Okay? So there's no problem with linearity. It seems to be doing the same thing. And if you look at the line that's fit on the left-hand side, the black line that's going across there, you can see that that does not have a very large slope in it. Look at the percent linearity that you see there. It's labeled B. That's 4.8%, not very high. Again, that value is very, very small. Is it statistically significant? Well, we would look back at our slope that we tested. Now, under there, you see gauge bias. And what it's doing here is it's giving you the bias and the percent bias that I showed you how to calculate earlier for each reference value. The average, the overall average, is the first line that you see there. But then you see the bias for each one of the individual parts. So you've got 5 things sitting there. The bias and the significance of the bias for each individual part and for the overall average. Each of our p-values here, okay, each of our p-values here are quite large. And again, what we're testing is that in this case, bias equals 0. That's our null hypothesis. I cannot reject that null hypothesis in any of these cases. So for each individual part reference value that I have, there's no significant bias. Okay, that's what you see when I have there labeled C. At the bottom, they've provided a plot that's called percent process variation. Again, it looks like, wow, linearity is really a problem compared to bias. But again, look at the scale that you have on the y-axis, on the percent. This is only going up to just over 4%, or just under 5%. So it looks really big, but then you got to take the scale into account to see was that significant. Okay? And I wanted to show you here just some hand calculations of where they're getting these values from. Okay? So if you look at the previous slide, or the values off the previous slide, what you find is, okay, for the percent linearity, they got 4.8%. Well, how did they get that? Well, the slope of your line was 0.04831. Process variation, remember we got that from the gauge R&R study, was 17.9631. And we get linearity with 0.8678. Okay. Now, percent linearity is just 100 times the absolute value of the slope, which is 4.8%, approximately. The percent bias, for one of the parts, I said part 1, with the reference value 2.1, here's how they got this value, 0.5%. Bias is negative 0.09. So the percent bias equals 100 times what you see there, the absolute value of bias over process variation, and you come out with 0.5%. So those are just some of the calculations, so you can go back and see, well, how did they get those values? All right. So now with all of that in our example, what we see is that overall bias is not a significant problem. That is, the gauge does not appear to be biased with respect to any of the reference values. Okay, the individual reference value individually. There also does not appear to be a problem with the linearity across the range of the measurement process of the reference values on the average. But, and this is what's not indicated by this, is look at the individual bias values as you move across. Back, when you get a chance, go back to the slide that we have with the bias, individual bias plotted against the reference value. You notice again, it was increasing as you went across. Okay? There may be an indication, but what happened was the reason that linearity in the bias did not turn out to be significant there is because you got to see it seems to be consistently above and below, so it cancels each other out. So those are a couple of things that you might want to look at. It's always good to look at the graphs to make sure that you're looking at the scale to see what am I really looking at, how significant is this. Then you can run some tests to look at, well, how significant is the bias, how significant is linearity.